Good morning. This is Mark Anderson from Staddies in Minneapolis. Welcome to a talk on leading edge experiment design for aerospace. As a first order of business, if you would look at your control panel, there is going to be a little hand button. If you press that, then I know you can hear me. So please press that raise hand button on your control panel. All right, Joseph, Marson, Andrew, Passant, I'm getting lots of good feedback. Thank you for that. I'm going to go ahead and put the hands back down again. And from time to time, I'll just check to make sure you're with me. You can also put in chat, and at some point or another, I'll get that, but maybe not till the end of the presentation. So those are a couple ways that I can get feedback from you. So let me start my presentation from the beginning. So again, my name is Mark Anderson, and I'm a professional chemical engineer, so I'm not an expert on aerospace, but I have worked quite a bit with companies in aerospace, such as Boeing and many others like that, that are working with the design of experiments, and also quite a bit with people doing wind tunnel experiments and things like that. So I will present a number of little case studies here that relate to aerospace industry, but basically the experiment design technique, which is a multi-factor testing approach, is going to work for any type of product or process development, not just the aerospace. I'm also a certified quality engineer, by the way, done a lot of plant process improvement work and that type of thing. My position now with Staddies is engineering consultant, and I'm operating, at the tail end of my career at about a half-time rate and pitching in to help Staddies as much as I can by giving presentations like this, providing stat help, doing training, and that type of thing. As many of you know, I'm also the co-author, actually the primary author of 3 books on DOE Simplified, RSM Simplified, and Formulation Simplified. So those are my credentials. Feel free to contact me with questions after the presentation. My email is mark@staddies.com. So the whole situation here for this industry or any industry is that it's important to do empirical studies. And as Tex Johnson at Boeing said, one test is worth 1,000 expert opinions. So it's really important to have those expert opinions to start with, but then put the opinions to the test. So again, welcome. I appreciate you coming on board here for this presentation. It also will be recorded and available afterwards, and the slides will be posted after the presentation. The attendees are on mute just to avoid, the problems of having voice over internet protocol, reverberations, and all kinds of embarrassing things that can happen when you have your microphones open. So instead, if you want to type in some chat, after the session, I'll spend some time and pick up those chats and we'll address those questions. Or, just make notes of your questions and send them to me afterwards. I'll get right after it. The presentation, as I mentioned, will be posted in the webinars part. So if you want to go back and study some of the slides or go back and listen to my presentation again, feel free. So again, at this point, I'm going to ask if you would press that raised hand button if you're still with me. So go ahead and press that button again. Okay, great. Again, we've got Andrew and Passant, and who do we have? Farama, Joseph. Okay, Merrick, there's too many to read them all off, but I've got a good sampling of, attendees, so that's what's important. I love statistics because from a few you can infer the many, from the sampling. And it's not exactly random, but I usually have a few people in the audience, I call them the canaries in the coal mine, that'll put their hand up and let me know that we're getting through. All right, so now let's continue on, and this lays out what I'm going to be discussing, and it'll be done within the hour and probably well within the hour, so we have time for questions at the end. But my main message, as always, is the idea of doing multi-factor testing versus one factor at a time, or what's called OFAT. And unfortunately, the OFAT is a scientific method, and most highly educated scientists and engineers are taught to hold everything constant and change only one thing at a time. But the key to success is to change multiple things, but do it in the proper way, using the correct matrix of test conditions. So then, of course, our focus on this presentation is on aerospace. So basically, I just kind of collected up various case studies by the type of design of experiment. And I've got actually a couple on factorial. One of them is a completely randomized experiment on a bearing, and that's going to be used as kind of an introduction. And then I have one that has restrictions in randomization to deal with hard to change factors, and that's called a Splitplot. And the one I'm going to show you is a fun paper helicopter experiment that we did. We've used this for training for our own workshops from time to time, and also for some workshops at various places like the South Dakota School of Mines and Technology. We do a paper helicopter experiment. It's a very good way to learn about design of experiments. And I was first introduced to this by George Box at a seminar in Madison, Wisconsin in 1996. Then we'll progress into a more advanced technique called response surface methods, or RSM. And this is an optimization tool. And we'll look at a case study on a jet fighter wing. I think it was actually on a computer simulation. And the other one on response surface is a split plot with hard to change factors on a flap design. And again, some of these are done in actual hands-on experiments, like in a wind tunnel, and others are using finite element analysis simulations and things like that. But it works really well to apply these tools of design of experiments to derive the transfer function or model, from your process. And then finally, we've got one case study that involves mixture design and also combining with categorical levels on a composite material. So those are the main tools that we're going to cover. The factorial design is used for screening and characterizing interactions. And then the response surface is used for optimization. And then mixture design is used, of course, for formulations. So there's a whole strategy here, and it's important to pick the right design. And then we'll wrap up at the end, and hopefully maybe a few questions that come in on chat. We'll talk about that. So let's begin with a really fundamental experiment, and this was actually reported by George Box in quality engineering, I think it was. And Box had a student of his, and the student's name was Christer Hellstrand. And Christer came over from Sweden. He worked for SKF and studied under George Box. They were having a lot of issues with this bearing. The Japanese had come in and they were taking away the market. This would have been back, in the 1970s when the Japanese became ascendant. And SKF was losing their business on bearings that they had been producing since the early 1900s. And the one factor at a time approach was not succeeding. But here's what Christer found out. He found out from George Box that you can do multiple factors at the same time. And he learned about a technique called two-level factorial design. And this was actually developed by Box's father-in-law, Ronald Fisher, in the 1920s. And coincidentally, I went to a centenary for George Box a couple of years ago in Madison, and I met Joan Fisher, who was Fisher's daughter and was married to George Box. And Joan Fisher showed up in Madison for the presentation. So I've had the privilege of, having some tutoring from George Box and meeting Fisher's daughter. These two, Fisher and Box, did tremendous things in the field of design of experiments. Box went on to invent response surface methods in 1951. But this is a more fundamental two-level design that dates back to the 1920s. And amazingly enough, people like Hellstrand and SKF had no clue about this because they were stuck in this corner of one factor at a time. And basically what they were trying to do is get a huge increase in the life of the bearing. Let's say the goal was to increase this accelerated life by at least 40 hours because the Japanese had gone so far ahead. So they looked at three factors. They looked at the heat treatment when they're producing these bearings, and they went from low to high on that. And when they did this one experiment, one factor at a time, they went from 17 to 25. Well, that wasn't enough. So then they turned their attention to a second factor, and the second factor was something called osculation. And osculation is the kiss of the bearing to the cage. So that was factor B, and they went from a low to a high level on that. And they got an increase, but it wasn't enough. And then finally, they looked at a third factor, which was the material that they were using. And I think they went from metal to a plastic. You can see the plastic raceway here. So I think at this level was plastic. This was a categoric factor, and this was metal. But it wasn't enough to get the increase of 40 hours, at least on its own. And so they were stuck. But then when Krister went to talk to George Box, he said you can do this two-level design, and you can do a two-level design represented as a number 2 on the three factors, which is the exponent. And of course, 2 to the power of 3 is 8 combinations, or 8 runs, we call them. And all this whole time, you've probably been saying, Mark, and you'd like to raise your hand and probably yell at me a little bit here, because look, there's an increase that's way over 40 hours, but it requires a combination of A and B to get there. And it actually turned out that there was possibly an advantage to the plastic as well, but it wasn't as much as you might think from this range here, because the variation of the life goes way up as the life goes up. And I'll show you that when I demonstrate the software. So that was the key. And of course, why would you just do one factor at a time when you can do multi-factor testing? And you're going to be able to then see the potential of interactions in this case, which is a synergism. And sometimes, of course, you see bad interactions, which are antagonisms, but that's good to know as well. So that was a really important breakthrough. But there's also another advantage we get with multi-factor because of its parallel processing over the one factor at a time, which is serial processing. You get a great improvement in efficiency. I'm going to erase all these scribbles, and I just want to point out what I'm talking about here in terms of efficiency. It relates to the power of the testing. And of course, we all know that sample size 1 is not going to help us for any type of statistical testing. We need to build up some averaging. And what's cool about this layout here that's represented by a cube is you actually have 4 at every level. For example, you have 4 at the high level, which is the right side here. And you have 4 at the low level of A, which is the left side. And then similarly, you've got 4 at the high level of B, which is the top of the cube, and 4 at the low level of B, which is the bottom. And C also has 4 in the front and 4 in the back. So every time you're doing a 4x4 comparison. And it turns out also that the interactions, like the AB interaction, which are operating off the diagonals, are also 4x4 comparisons, but it's a little hard to show with the geometric representation. It's easier to show in the matrix. Now, the OFAT experimenters, for example, the engineers at SKF in Sweden, could come back when Krister tried to explain this technique to them, and they could say, well, yeah, but we could do 4 at the baseline, and we could do 4 at each of the high levels. Now, we wouldn't see the interaction that you found, but at least we get 4x4 comparisons. However, as you can see by just counting up these green dots and knowing that there's 8 corners in a cube, the OFAT, to get the same power, is going to have to run twice as many runs as the 2-level factorial DOE person. And this efficiency, which is 2 to 1 for 3 factors, actually increases as the number of factors increases. So you get a steady increase in efficiency as the number of factors go up. So for example, you can run these troubleshooting experiments on 8 factors, and you can even use a fractional factorial, and you can do 8 factors in 16 runs. and it would take forever to get that same power of 16 runs with 8 at the high and 8 at the low if you're doing just one factor at a time. So really, I mean, since I've been doing these two-level designs for decades and decades and decades, whenever you get anywhere near close to where you want to be, it's just incredibly inefficient to just do one factor at a time at that stage. So let's go ahead and take a look at the tool, which is Design Expert, that Statis is the developer and publisher of. And I'm going to pull that up. By the way, we had a lunar eclipse, and that's what the picture is from the astronomy picture of the day across the United States early this morning. So I'm going to open up a file here, and this has actually got the layout in random order of the bearing results that I took from George's Box's publication. Now, the actual levels were not revealed by SKF for obvious reasons of confidentiality. And I'm just surmising that the metal and plastic was the cage material. They didn't say that for sure, but they did give us this life in hours. And you notice that there's some tremendous increases here, which I've highlighted in blue. Now, the way that this is set up is very easy using Design Expert. I'll just show you by recycling this data. You start with this really handy color-coded grid where the full factorials are in white on this diagonal. And obviously they're going up by powers of 2. Where we're at is just simply 3 factors and 8 runs, which is a full factorial. But as you get up to, say, 5 factors, it pays to cut back, particularly to the green shaded designs that are high resolution. And these are good for characterizing 2-factor interactions. And I mentioned, the idea of doing 8 factors, which would be ridiculous doing all the possible combinations at 256, but you could start cutting it down in half by 1/4. But you could go all the way to this 1/16th design if you're willing to go into the yellow zone. And those yellow designs are good for what's called screening. So you might screen first, many factors and see if you can find a vital few from previously unknown ones, and then follow up with a more in-depth study on the vital few that emerge. So there's a whole strategy. That's not the topic of this talk, but if you look for a talk called Know the Score in the webinars that I presented at the DOE Summit a year ago, June, you'll see a good layout of strategy of experimentation. But again, I'm kind of focusing on aerospace. I figured bearings, would relate to that in terms of being a mechanical aspects of it. So what we're going to do then is pick this 2 to the 3rd design, keep it simple. And then all we have to do is just put the names, the units of measure, which I don't have because it's confidential. And normally I would put these in as numeric factors, but we only have, these placeholders, because of the fact that they wanted to keep these secret. But it's very easy to enter that in. And then what's cool is we have this power calculator. So let's say that we were interested in trying to see a 40-hour improvement in the life. And our normal variation, let's say, is 15 hours on this accelerated test. Then, for example, even with the 8 runs, with this signal to noise ratio, which is actually pretty high, we have an appreciable probability of seeing that difference of 40, even though we have a noise of 15 in the overall testing, just because of the process variability of doing life testing, the measurement, and so forth, we've got variation. And we recommend at least 80% or greater. There's nothing sacred about that number, but obviously the higher that is, the better to a point. You don't want to get it too high because then you're probably overpowering and spending too much time. So then we finish, and now we have this layout. Now I'm going to go ahead and open up this file again. And I don't necessarily want to spend a lot of time on this, but some of the things I would do is I would sort, and I would see that there's, of course, more than a 40-hour increase, which is making me pretty happy. And I'm getting some ideas of what's going on here because of the fact that I'm seeing the modified oscillation, which is a high level, and the high heat being the main thing. And metal and plastic are not as much of a factor just by inspection. Now, the interesting thing about this data is because of it increasing so much, the variability is not constant, which is one of our assumptions. And so it pays actually to do a transformation of the data. And so even though we see these standout effects here, and the p-values are very good, and the r-squareds are high, there's a diagnostic, and wouldn't you know, it's co-invented by George Box, that tells us that taking a log of this data will give us a better fit. So seeing that, if you go back and the program provides this transformation, you could either do natural or base 10. I'll do the base 10 log. When you do that, it turns out that you get a cleaner separation in the half normal plot. You get higher bars on this Pareto chart and lower p-values and higher r-squareds. And then the diagnostics that we see turn out to be far more normal than they were before. So that's one of the keys to analyzing this data, is taking the log transformation. And then what you see is the interaction is showing you that the effect of A, which is oscillation, depends on the level of B, which is the heat. When heat is at the low, which is a red line, you don't see much of an effect basis of these least significant difference bars being overlapped. But then when you switch to the high heat, which is a green line, you see this big increase. Now also the variability of the life increases, and that's why this bar is wider. So I'm just gonna stop here for a second and just ask if you guys appreciate, seeing this big increase in the life as much as the SKF. Well, maybe you don't see it as much as they did, but I'm sure you appreciate the advantage of multi-factor testing. If you agree with the multi-factor testing as being an advantage, press that raise hand button. Okay, Andrew, thank you. Good for you to weigh in, Robert, et cetera, et cetera. And I could be preaching to the choir here to some degree, but on the other hand, if you already know all this, maybe this will give you ammunition to convince some of your colleagues and people in your professional fields that they should not be doing the one factor at a time, other than really fundamental kind of blue sky type work. But as soon as they get close to their goal, they should start doing this multi-factor approach. Okay, so now let's move off of this. And I just want to give you a nice little postscript from SKF, kind of the rest of the story. It turns out that when they had nearly gone out of business at SKF due to this Japanese competition, once Christer found out from George Box about this two-level approach, they abandoned the one factor and started doing this multi-factor. And as a result, they improved their bearing life tenfold, from 41 million to 400 million, and they reduced the cost as well. And you see the quote from George here. Christer showed them how they could test 2 additional factors for free, basically, because with the multi-factor approach, you can get more and more factors in within the same number of runs and maintain the same power. And that's what they did, and it worked. And there's a couple of references here that I got this from. Again, you'll have a chance to go back and pick up those slides, and then you can follow the links. So now I'm going to segue into another factorial design, but this one has hard to change factors. And so we're going to use a design that Fisher developed called a Splitplot. It comes from the fields of agriculture. And you would, for example, if you're going to take an old biplane and spray fields, it's going to overspray on each field. So you probably want to split out the switchover from the tank for one herbicide to another and restrict the randomization of the application of the fertilizer, and then randomize within the subplots, which are the fields, the other factors like the type of agricultural crops and things like that. So this is something that you need to study a little bit, but it's a super helpful tool for engineers like myself, or even if you're working in the kitchen doing experiments and you don't want to run every single cookie at the different time and temperature in the oven, you can restrict the randomization so that you do a batch of cookies, per oven setup. And so it's a tremendous tool. I'll show you how it helped us in studying this paper helicopter experiment. A picture of it is shown here, and we do this in class. We look at the different wing lengths and body lengths and different types of paper. You can put a paper clip on or off. You could drop it from the bottom or the top. And then we see how close it comes to the target and how long it flies. So there's actually two responses. Well, it turns out that the design of the helicopter, which involves some cutting and folding and so forth, is the hard part. And so if you're able to restrict the randomization by declaring these design elements hard to change, and then the easy to change is actually whether to put the paper clip on or off once you've built the airplane, and then dropping it from the bottom or top, that's easy. So we're able to restrict the randomization on this using a split plot, and I'll show you what I mean. It'll be more clear when I pull this up. So let me close this out. And we'll open up the paper helicopter experiment. Now notice, I'll show you how we build this in a minute, but notice the layout of this. There's a lot of information here, but the small case letters relate to factors that are design elements, like the paper type being this standard copy paper called Nav Ultra, which is 24 pounds, or we would use this Conqueror X22, 26.6 pounds, which was supposedly used for the world record airplane toss. So I picked up a ream of that and compared it to our normal office copy paper. But every time you see a black line, that's a little grouping. And so each one of these groupings includes one design of the helicopter. See that? So in the first group, we've got the Nav Ultra with a long wing, short body, and narrow body width. Then once we had that airplane built, we actually would drop it either by putting a paper clip off or on from the top or the bottom, and then measure the time of the flight. And then we would measure after 3 drops what the standard deviation of that was. And then each time we dropped it, we would measure the distance from the target and average that out, and then take the standard deviation of that. So every one of these results for the time and for the target deviation is based on an average of 3 drops. So then we completed that part, and then we went to the next design, which is number 2, and we would actually label the helicopters with a Sharpie, 1, 2, and so forth. So here's the second one that was designed, and we had actually one person in the office build the helicopters for us, number them by the group number, and then we had, a little team of computer programmers and engineers, and I took the job of typing the data in since I didn't want to climb up the ladder and drop it or crouch down on the floor and measure the deviation. So I picked the best job, which is just collecting the data into the computer. Now, the way this was built, I'll show you, it's really easy with Design Expert. So now we're going to move off this randomized part, where these are fully randomized designs, and we're going to go into the split plot section, where we have a number of hard to change, and in this case, we've got 4 hard to change factors. And this is actually going to be done in a full factorial, but by grouping, we're able to save quite a bit of time by not having to build a helicopter each time over and over, but rather grouping saved us quite a bit of time for the whole experiment. There's 2 runs per group, and this actually ends up being a high resolution because of the green square. I can tell that, and it's actually only a half fraction of all the possible combinations. So we're going to have 16 builds of the helicopter, a total of 32 runs, each one's dropped twice. And that's how we built this up. And here are the names of the factors that we typed in. Again, these are categoric, but you can put in categoric or numeric. So very straightforward. And the responses, we were being very thorough by dropping each one 3 times and taking the average and entering that. And you could do a power calculation very easily on this. But since we've already got the experiment completed, we'll just pass that one. And there's some issues when you group like this that I kind of skipped over, but it does turn out that you do lose some power on the main effects of the hard to change factors. You do lose some power on that, but on the other hand, you gain power on the easy to change, and you also gain power on the interactions of the hard to change and the easy to change. But this goes way beyond what I can try to tutor everybody on right now. But do look into the Splitplot because it's going to save you a lot of time, and make sure you understand, what the ramifications are, because there's never anything free in statistics. When you restrict something, you lose power on it also. But it was actually a good trade-off for us, and we went with it, and it worked just great. We ended up, finding some significant factors on both the subplot, which is with the easy to change factors, and also on the whole plot, like the wing. The wing length was a really big whole plot, hard to change factor that really emerged. And then we also had a little interaction between the paper and one of the other factors, whether the paper clip was on or off. So there was a little interaction there that was kind of interesting, which I'm showing right now, that when we switch to the really good paper, which is the green paper, then to get a longer flight, we didn't want to put the paper clip on. And I'm not sure how significant that really is, but there's a little bit of a switch over depending on what paper you have on whether you want to put the paper clip on or off on the time. And then also on the target deviation, let's see what happens there. There were some other interesting impacts as well. And we have all the capability of doing the p-values using a specialized tool called restricted maximum likelihood. We have some, R-squared values. We have most of the diagnostics available and everything else. So this split plot is something I think that's really good for aerospace or any type of mechanical industry, but it's also good for process industries like oven temperatures and things like that. And then ultimately, we were able to discover ways to minimize the time, well, maximize the time, I'm sorry, we want to maximize the time of flight and minimize the deviation from target. And then the program dialed up a solution, and it turned out the Conqueror paper, which is the better paper, did come out ahead. Wing length, long, and so forth. So this specifies the build, and then it actually turned out better to have the paper clip on because it made the helicopter go on target better. It stabilized the flight. So that's an example of aerospace, although it's a paper airplane. And then if you get a chance, when you get this slide deck, follow this little link here because it's got a very interesting write-up about the perfect paper airplane. And it even has this really cool video. I wish I had time to show it, but I don't. But do take a look at the slides and follow up on that link. Okay, now moving ahead to response surface, which is a more advanced technique. Now, I don't have personal knowledge of this experiment. I was not part of the team. But I did write this up in one of the books, and I'm the primary author of, which is the RSM book. And you'll find, this in table 4. And they use what's called a face-centered central composite. The central composite is comprised of the factorial with center points. And normally you put the axial points outside of the box. And this is a design that Box and Wilson invented in 1951. And they had suggested you go outside of the box, but a lot of people have trouble getting that far out. So they do it as face-centered, and they bring these stars into the face of the square. And in the case of 3 factors, that would be a cube with points at the centers of the faces of the cube and points around the perimeter of the cube, and then some points in the middle, which are the center points. Now, this design is easily set up in Design Expert. So let me close this out and open up the wing case. And then I'm going to make this a little bit bigger, and I'm going to display the point type. So we can see, now this one is entered in the standard order because I didn't have the actual random numbers. So never mind that, it should be done in a randomized plan. And over here is the response, which is wing weight in pounds. Now, just as making one of my occasional checks, are you able to see this design with the aspect, taper, and thickness factors, the wing weight, and the space type? Press that raise hand key, please. Okay, Andrew, we're off to a good start and going on from there. Thanks, everybody. So we're still be able to see this. That's good. The internet is working. Now, the analysis of this, it looks like it's been a while since I've worked with this when I wrote the book on RSM back in 2006. So I'm just kind of winging it, pun intended, at this point. But what happens is the program will provide you with a series of models all the way up to the model that you've designed for, which is quadratic. And based on the principle of parsimony, sometimes it'll actually recommend a lesser model because you don't really need to continue going up in order of terms because it doesn't significantly improve the fit. And the R squared values don't go up. So why bother? In this case, once you go to the linear, and I think this is in log scale, that suffices. And then you have your usual p-values, R squared values. The diagnostics, you can see the box Cox is actually recommending the log, and that's why we did that. So another one that's in log scale is very common. And then it looks like I tried another model that I reduced using quadratic. Now the new version 13 makes this easier. You don't have to have separate columns of response. You can just press this plus key. So 13 makes this comparison easier. This model is also usable, but it may not be as good as the log scale. Let's just look at the adjusted and predicted R squareds. So I think the log model is better, and then I would use that and just let the program, tell me what I want, whether it's to maximize or minimize or whatever the goal is. We can type that in here. Now, with these response surface methods, you can develop more interesting looking plots. If we look at it in the quadratic model, it's going to be a little bit more interesting, perhaps. Let's look at the 3D. Okay, well, it doesn't have much of a twist to it. So this is not the most exciting results, in terms of having a really cool surface, but it worked. And this came from a physics-based finite element analysis simulator, which is interesting. And coming up later this year, potentially, we're going to come up with some tools that develop better designs. What I recommended in the RSM book is using optimal design, but then over-specifying the model by 50% to get some space filling. But moving forward, we'll be coming out at Staddies with Latin hypercube designs and things like that. And also better ways of analyzing different types of simulations, particularly those that are not random. So here's another one, and this one is from Kowalski, Parker, and Vining's book, Tutorial on Industrial Splitplot Experiments from Quality Engineering. And it was a real wind tunnel experiment on an aircraft flap. And this one is a split plot. So this one has, again, the hard to change factors in the lower case, which are the gap and deflection angle. And then we have some easy to change configurations that affect the lift. And then this one uses I think, the full central composite to accomplish your mission. So let's see what we have here. Actually, I don't know if I have this one, aircraft tutorial data. Okay, let's airfoil tutorial data. Let's see if that's in here. Help tutorial data, airfoil. Okay, here it is. So this is actually a tutorial that we have in the program on response surface Splitplot. I wrote this tutorial, but I forgot about it. So there it is. And here's a picture of the wing and the trailing flap. And so this actually is in the Design Expert program, and you can run through this complete tutorial yourself and reproduce the results. So now I'm going to go ahead and open up the data. And in the notes, I've got some information here recorded. And then here's the layout of it. And you can see the grouping with the black lines in between. Now the grouping on this one is variable. In other words, there's different numbers in each group. So this would have been done with a different type of a split plot using the central composite. So now let's see if I can figure out how this is put together. Reuse the same factors. Okay, so here it is, central composite. It's under the split plot, whereas, we have these randomized options of central composite box Mencken, optimal design. Here we also see the definitive screening, which is like a super saturated design, but it fits more under response surface and factorial. But we're under the split plot where we've got hard to change factors. And let's see, we've got 4 numeric factors. Okay, I guess this one just has the one gap that's showing as hard to change. And then as you press forward, it would design the experiment. Let's go ahead and reopen the file. Okay, that was under airfoil, tutorial data. Okay, so there's actually 2 that were hard to change. So when it recycled back around, it didn't show the second one was hard also. So now when we look at the results, you'll see that this models it for you. You can do auto select. And for example, we could look at the p-values and take out the worst p-value, the next worst, and so forth all the way along until only p-values that are less than 0.1 are left. And that would reduce the model. Maintaining hierarchy, to support the higher order terms by putting the lower order terms in. And then you can see the statistics that are provided by the program. Diagnostics are provided. And then here's a picture, a more interesting picture of, let's say, the 3D surface. And then you can slice on other things here. And you can also change the color coding on this. I think my notes suggested that if we change the color gradient from -400 to +200, so you can change this color coding gradient. You can even reverse it for the people in UK that go the other way around, and you can get different colors as you slide around. And then you could do some kind of numeric optimization, and I forget what the goal was, but it must be written up in the tutorial. Okay, then last but not least, I have one more that involves mixture design, which is very important. For example, the people making composite materials or any type of plastics, metallurgists, chemists, are going to be using mixture design to optimize their formulation. So this one was an epoxy fiber composite, and they had a differing range of elastomer and fiber. And then they also had hardener and epoxy resin, which we're just letting float when we enter it in. But we have a multi-component constraint to make sure that this epoxy to hardener ratio, C to D, stays within a certain range. So this is a well-crafted experiment using tools and Design Expert. The categoric comes in because there's 2 types of elastomer and 3 types of fiber. And this is one that we've used in our workshop, mixture design for optimal formulations. And I'm not sure if it survived into the distance learning mixture design when we switched from in-person after the pandemic started, and we had to scale back a little bit to avoid the Zoom fatigue. But it would be in the in-person class if we get going on those again. So let me close out the current design that I've got up here and open the composite and then control mouse wheel to make this smaller, and you can see the entire design. And you can see the components here, 1 through 6, well, 1 through 4, those are percentages. And then over here are the categoric types. So like this elastomer at 8.98 is using elastomer 2, and this fiber at 57.19 is using fiber 3. So that's how this is laid out in a randomized plan. There is a rounding, by the way. You could round this even further, which might be useful. And there's a couple different ways by decimal places. I guess I should have. So that's a tool that we have in there as well. Then I would probably just change the formatting to not put the .00 on every number. So now I'm going to open this up again, though. I'll close it because I probably would have affected the results there. Yeah, you can see doesn't like some of the things I did when I rounded. So I'm not going to save this. And here it is again without the rounding. So we'll leave it like that. Now, the way this is built is it's going to be what we call a combined design, because it combines elements of mixture with 4 mixture components and categoric with 2 of those mixture components being with different categories of material types. You could also put in numeric factors like time and temperature. I'm not going to do it here, or even another mixture like a coating on top of this composite material could be also included, but that would be a lot of things to experiment on. So there's plenty already. We're leaving this as easy to change, but obviously you could consider doing a split plot that would have, let's say, hard to change mixture that would be batched and easy to change materials, or vice versa. So there's lots of considerations there. Also, there's a special constraint in here that takes care of the ratio of the last 2 ingredients. That's under this little button called Edit Constraints, and you can actually put the ratio that I'm showing here directly in, and it'll parse that out. Okay, now this is an optimal design, and we're using something called a KCV, or Kowalski-Corning binding model, which is a really cool way of reducing the number of possible combinations, but still getting an idea of interactions between the mixture and the categoric factors. So it actually reduces the number of runs quite a bit than if you did an old-fashioned cross model, like if we did quadratic by 2FI, it would go up to 70. But by using the special KCV model, we're able to reduce it down to only 34. So that's another advantage. Here are the 2 responses. We could size this design using fraction of design space, but I won't go through that because I'm going to run out of time here pretty quick. Then the program, sets up your experiment by doing, an algorithm searching through coordinate exchange or point exchange, or both. And then it comes up with a good, set of combinations that will fit the model that you're asking for, which is this specialized KCV that will help you estimate interactions of the ingredients with the types. I haven't looked at this for a long time, so I'm just winging it again in aircraft terminology. I'm winging it. And this little ladder selection process that Design Expert provides already has suggested that I could go with this quadratic mean model. However, it's going to end up being a KCV in any case, because that's what we set it up for. And from there, we could auto select and reduce down the terms, and we get a reduced model here. That's the specialized KCV model. And it looks like it's giving us, good p-values, no significant lack of fit, good adjusted and predicted R-squared. The diagnostics in terms of normal plot of residual versus run and box Cox are all good. And then we've got some fun to work with here because we've got various combinations, 2 by 3 or 6 different combinations of materials. So this would take a while to kind of sort out, looking at the different types of materials and the different slices of epoxy resin. And got a little paper airplane here. How about that? And then we would do the same thing with the tensile strength. I'm just going to kind of rip right through this with the KCV model, do the auto select, accept that, check my stats, diagnostics, and then, we would do again, more model graphs and have some fun playing with that. Then in the end, let's see if it says maximum impact 100 to 140. So we want to maximize the impact, and 100 to 140. And then the tensile, the goal is 1200 to 1400. I think, maximize that too. 1200 to 1400. And then here's the solution. So it says 9.1 of elastomer 2, 62 of fiber 2, 9.32 hardener and epoxy resin, and then that gives us, the most desirable combination of impact and tensile. Let's see if I can see this on the graph overlay. If we say we have to have at least 100 impact and 1200 on the tensile. So here's a little window or a sweet spot, and if I move epoxy resin around, it starts to lose out on the impact. Let's go back to solution number 1. And then what happens if I switch to the first elastomer? There's a smaller window. So second elastomer is giving us a bigger window. What about the fibers? Okay, fiber 1 has got a window, but it's less. So it looks like there's actually other considerations we could come into play here, like the cost of the different materials. We could work that into the equation. And there's a lot more we could do, with this example, but we'll quit while we're ahead. Okay, so conclusions. It's not magic. I found this little drawing of an airplane for somebody like me that's a chemical engineer that's not an aeronautic engineer. So it's like magic. There's air coming in, very important magic, more air, more magic, some more magic in the back. But it's really not magic because the engineers that are designing these airplanes and the chemists developing the composite materials and all that, they've got a great deal of subject matter knowledge. But then using this multi-factor testing approach, you'll be able to more quickly converge in on, where that sweet spot is. So definitely it's going to be good for all the engineers and scientists working in this aircraft, space, defense industries to apply this multi-factor design of experiments. And you can use factorials to screen and characterize, and you can also deal with harder change factors by using the split plots. And then response surface methods, or RSM, for the optimization, and I showed you an example of that with the wing design. For the factorials, we had the bearing case, and then the paper helicopter, which was a split plot. And then response surface methods, I showed you split plot. Then we looked at mixture design, and it was actually a combined optimal design that looked at categoric materials, for the composites. So hopefully this gave you a good demonstration of the different types of things that can be done using the tool of design of experiments and response surface methods and mixture design, and using Design Expert to accomplish that makes it really easy. So I'm going to just finish off by letting you know that we have various free webinars that you can attend. From time to time, we do this crash course for experimenters. Check this SC site on webinars to see when the schedule is. And we also have a new user intro that we do on a regular basis. So take advantage of that. If you haven't had training, or even if you have and it's been quite a while and you need to resharpen up your DOE skills, we have some core classes. The modern DOE for process optimization, that covers the factorials and the response surface methods. The mixture design for optimal formulation, obviously, is the mixture experiments, and plus combined experiments combined with mixture process and things like that. Or we can do a private class for your team. And that allows you to choose your own date and time. Nowadays, it's mostly being done at a distance, but we'll probably get back to in person very soon. Now that the pandemic is waning, people are getting vaccinated, thank goodness. And then individuals, we've got public workshops, and you can check the schedule for that. If you would like to get a quote on a team teach, check with our workshops at this address, workshops@states.com. Okay, well, that concludes my presentation. I'm right at the top of the hour. So we'll consider this to be mission accomplished, I hope, and maybe just give me a signal on your screen that you appreciated, learning a little bit about these applications for aerospace by pressing that raise hand. And then I can see that there's going to be some questions coming up in some chat. So those of you that want to ring off, just go ahead, and it's been good to see you and talk with you. Go ahead and just ring right off and head on to the rest of the day, that you've got planned out for yourself. Others that would like to stick on for a minute, I'm going to start taking a look at some of the questions here and chat. So I'm just going to go off the top of the list. I'm going to click question from Basant. And he says, or she, theoretically, ANOVA should be followed by a post hoc test such as Duncan's or LSD to find where the significant lies between levels of a categoric having more than 3 levels. The testing post hoc, basically we're using the idea of the protected test, using the F test to begin with to kind of protect yourself against doing the pairwise comparisons afterwards. And I've written up, some discussions of that in my newsletter called DOE FAQ Alert. You could go back and look through some of the old DOE FAQ alerts for discussions, that include input from master statisticians. So the methodologies that we provide, for assessing overall model significance and then individual factors does work even if you have multiple categories. But I would suggest, Basant, you may come back. I'm going to write something down on the slide here, because I think what you should do, my real brief answer, because I'm not a master statistician, I'm an engineer, doesn't satisfy you, is go to the stathelp@states.com and email your question there, because that'll go to our staff that includes a PhD statistician. But I'm certain that what we're doing is correct, and we don't need to do these, post hoc tests. We do have least significant differences on the interaction graphs, by the way. So I'm just working through now some more questions, and let's see if I can make this bigger. Okay, Farama says, hello, I want to optimize an extrusion process with composition, fiber content, compatibility, compatibilizer content being variables. So I have both processing variables and formulation. Should I use a mixture design? Well, Farama, what you're going to do is something, what I did with the composite is you're going to use a combined design, and the processing variables will go, I'll show you. So you're going to go to this optimal combined, and you're going to have, some number of mixture and then some number of process. And so that's actually a pretty easy thing to set up, and that would end up being an optimal design. But here again, Farama, if you want to go to our stat help at stathelp@statease.com and get really specific on exactly what you're trying to do. If you're able to set it up in Design Expert first, and then send that DX file to the stathelp@statease.com, that'll save some time. But do give some description of what you're aiming for and get a second opinion. Mary is asking how many observations are selected when doing one at a time. How are observations selected? That's a good question. I haven't done a one factor at a time experiment for a long time. I do sometimes just kind of haphazardly before I start my design of experiment, select certain combinations of things that I think are the extremes using my subject matter knowledge and do what I call range finding. So that's probably about as far as I could go with that question. Manpreet is asking, do you recommend 4-factor CCD as I encountered in a few studies? Second order is fitted. 2 of the factors can be fixed, just an idea. Well, 4-factor CCD gets kind of to the outside point if you're doing actual hands-on experiments of what you can afford to do for the number of runs. I don't think 4 factors for doing a response surface method is out of line, but certainly when you get to 5 or 6 or more factors, you'd be better off screening and characterizing and narrowing down to just a few. So I think 2 to 4 factors might be good for response surface methods. And then he's following up with the 4 factors are temperature, time, solvent, concentration, pH. Yep, I think that could be a good response surface, but what I would suggest is that maybe you do a full factorial of 16 runs on the 4 factors, put a center point in at the center time, center temperature, center solvent concentration, center pH. And if you do 4 center points for a total of 20 runs, then you could check curvature. And if curvature is not significant, you'll end up with a lot fewer runs, starting off with the factorial design with center points. If the curvature is significant, you can use Design Expert's augment tool to then augment the design in a second block. And so that would be a better strategy of experimentation that allows you to possibly save quite a bit of time, straight away. Okay, I think that concludes the questions that we have. I want to thank everybody for attending this presentation and continue on with questions to the stathelp@statease.com. All right, everybody, take care now and good luck.